Welcome to a proof of the limit as x approaches 0 of the quantity e to the x minus 1 divided by x equals 1 using the Squeeze theorem. Notice if we try to determine this limit using direct substitution, we have the indeterminate form of 0 divided by 0. Because we'll be using the Squeeze theorem for our proof, let's begin by reviewing the Squeeze theorem. The Squeeze theorem states that if f of x is greater than or equal to g of x and less than or equal to h of x for all x in an open interval containing c, but possibly not at c, and the limit as x approaches c of g of x equals the limit as x approaches c of h of x, which both equal L, then it follows the limit as x approaches c of f of x must also equal L. Looking at this graphically, f of x would be this function in the middle that's always equal to or greater than this bottom function, and also always equal to or less than this top function on some open interval containing 0. And therefore, since the limit as x approaches 0 of this bottom function is equal to 0, and the limit as x approaches 0 of this top function is equal to 0, it follows the limit as x approaches 0 of this middle function f of x must also equal 0. So because we're trying to prove the limit as x approaches 0 of the quantity e to the x minus 1 divided by x equals 1 using the Squeeze theorem, we'll first graph this function, then determine two functions that would satisfy the Squeeze theorem. So in blue we have the graph of f of x equals the quantity e to the x minus 1 divided by x. This bottom function here, which we'll call g of x, is equal to negative absolute value of x plus 1, and then this top function, which we'll call h of x, is equal to the absolute value of x plus 1. Notice how the function f of x is not always less than or equal to this top function, but it is less than or equal to this top function on an open interval containing 0. So we'll only consider this on the open interval from negative 1 to 1 to satisfy the Squeeze theorem. So to set up our proof, we'll consider g of x equals negative absolute value of x plus 1, f of x is equal to the quantity e to the x minus 1 divided by x, and h of x equals the absolute value of x plus 1. On the open interval from negative 1 to 1, we do have that e to the x plus 1 divided by x is always greater than or equal to the opposite of the absolute, is always greater than or equal to negative absolute value of x plus 1 and less than or equal to the absolute value of x plus 1, which we just saw graphically, and the limit as x approaches 0 of negative absolute value of x plus 1 equals 1, which we can determine by performing direct substitution, and the limit as x approaches 0 of the absolute value of x plus 1 also equals 1, and that's all we need to show, and therefore by the Squeeze theorem, it follows the limit as x approaches 0 of the quantity e to the x minus 1 divided by x must also equal 1. So we do have our proof, but let's go back and look at this graphically again. The Squeeze theorem is satisfied on the open interval from negative 1 to 1, and because as the limit as x approaches 0 of this bottom function equals 1, and the limit as x approaches 0 of this top function equals 1, it follows the limit as x approaches 0 of e to the x minus 1 divided by x must also equal 1. I hope you found this helpful.